Okay, so welcome everyone to live session 12, Design and Analysis of VLSI Subsystem. I'm Kailash Prasad, PhD scholar from Nano Electronics Devices and Electrical Engineering Department, IIT Gandhinagar. And this is the last session for this course. And I have actually already completed the questions regarding the course and all. We also had a small discussion in the last session. So I wanted to have this session just such that you should know, right? What are the further opportunities you have in the VLSI domain? That's the first thing. And before that, what are the other courses you have to do to get an expertise in the VLSI domain? In the last session, one of the question that was asked in that regards only, and what kind of research that are going on. I will just mention couple of research which I am currently working on, and yeah, everybody around the across the globe is working on that aspect. Okay, so yeah, we will start with the session, but before that let me answer the question. Yeah, so the link is here. So this is the link of the YouTube playlist. So you can go and watch all the recordings and all the sessions as of now, whatever we have done. So yeah, let us start. So whatever we have done as of now can be just summarized using this 12 bullet points, right? This I've been showing from day one. And the idea of the course was to learn the VLSI design from the basics. You understand the fundamental concepts regarding VLSI design, and you go from the basic circuit designing to the final layout level to do all kind of functional analysis and the timing analysis corresponding to that. And for that you need to learn the concept. We have been discussing all of these concepts over here. In the week 1 and 2, we have started with the CMOS transistor and the current model. Then we learned that the most important circuit in the VLSI design, that's the inverter, right? So if you, I have already said that if you understand inverter, right, you pretty much understand everything in the VLSI design, right? So with the help of inverter, we have learned the noise margin. We have understood the delay. We have understood the power, and then we have started with more complex circuits for finding out the performance of more complex circuit. For that, we realized that okay, you cannot do directly the delay analysis of the circuit, so you need to have some model. Okay, so we have understood about the Elmore delay model. Okay, in the Elmore delay we have seen the L and pi model, and we have learned that okay, if you want to design, right, even if you do the modeling aspect of it, what you have to do, you have to later design the circuit. Okay, so the designing part was done using the logical effort. Okay, how do you appropriately drive the load, the final load? Okay, so once you are done with that, we go to complex circuits in the combinational circuit where you design AOI gate, OI gates, and various kind of dynamic circuits we have learned. So this was the front end of the part. Then we have moved to the back end where we have started learning about the layout, the stick diagram, and the most important thing is the interconnect, right? So which connects the two nodes or the two meeting layers. Okay, so after that what we have done was we have learned the power, because we have already learned the delay. So we have learned the power, CMOS latch, and the flip-flop design, and we have done the static timing analysis, because timing is one of the key constraint, right? So you have to make sure that okay, whatever the circuit you are designing, every signal is reaching at the correct time, right? And if it falls between the violation windows what we have discussed, like setup and hold, and then there can be problem of meta stability, the output won't be correct, the data again get lost. And the final part was the adder design and approximate computing. I will just give a brief overview of approx computing in the coming slides. Okay, now the question is okay, what are the set of the courses which you have to do to get an expertise in the VLSI design? right? So you are already doing an advanced VLSI design course. So I assume that you have already done the basic digital design course. Okay, even if you not done the basic course, so what I suggest that, okay, what you can do, you can go through this course from on digital circuit by Professor Santanu Chattopadhyay from IIT Kharagpur. And this, just like this particular VLSI design course, this course covers the very basics of the VLSI, the fundamental concepts regarding the digital circuit design, right? And if I have actually been TA of this course also in the earlier semesters, and if you want to say get your hand dirty and you want to try to solve the questions, you can go to my YouTube link, and there will be enough questions on digital circuit design. The questions are again designed in such a manner such that it will help you to crack interviews, and it will help you to also crack many competitive exams like GATE and all, right? So that's the first course that everybody should learn when you have been when actually you started learning, or you are seeing your future in the VLSI design. Okay, so that's the first thing. The second, and the one of the most famous course which is available in the VLSI design is the hardware modeling is using Verilog. Okay, so that's one of the very famous course. Uh, okay, the audio is lagging. Okay, is it the case with everybody? uh, the other people can hear my voice clearly? Can anybody please confirm that I'm audible?
Hello. There's something not clear, guys, personally.
Okay, yeah, just give me a couple of minutes. Yeah, I hope, am I audible now?
Yes, yes, sir.
I think there was some internet connection problem. I think I got disconnected. Let me share my screen again. Okay, yeah. So is my screen visible?
Yes, sir.
Okay, so yeah, what I was discussing is about this course, the hardware design for hardware modeling using Verilog, right? So this is one of the very famous course of from Professor Indranil Sen Gupta, again from IIT Kharagpur. And the course actually teaches you how to model the digital circuits using Verilog, right from the very basics, right? So the course assumes that you don't know anything about Verilog, right? You just have learned a basic of digital circuits, right? And if you want to design any complex circuit, you can take this course, right? So anybody who wants to have a career in VLSI, one of the very important skills he should have, that he should understand any one of the hardware description language, right? It can be Verilog, it can be System Verilog or VHDL, right? And this is one of the important course to go ahead. Okay, so please go through this course. Again, this course is available on NPTEL, right? So the courses which I'm showing are mostly available on NPTEL. Now the third course, right? So because what we have done, we have seen, okay, the digital circuit, you have understood the basic, you know how to design the digital circuits. But as a VLSI engineer, or as a semiconductor engineer, you should understand the semiconductors also, right? You should know that, okay, how the electrons are flowing and what kind of device physics is going on in the back end, right? I must say that, okay, in the advanced technology node and what the people are doing in the industry, the basic problems are coming from device itself, right? So and to tackle those kind of problem, you should have a very basics understanding, a very detailed understanding of semiconductor devices. Okay, and one of the very good courses from IISc Bangalore is there, that is Semiconductor Devices and Circuit by Professor Sanjeev Sambandan. Okay, and this covers actually course covers actually the basics of semiconductor physics, the operation of semiconductor devices, and how do you use these semiconductor devices to design circuits and systems. Okay, so they start with the basic quantum physics, very basics one, that whatever that is required to understand the semiconductor physics, and then they will go into greater detail of the basic concepts of the band gaps, right? How the PN junctions are made, what are the physics concepts behind that. Then they start with the Schottky junctions. Okay, then they will go ahead to discuss the BJTs, and then the most important thing is the MOSFET, which we use, right? We just take MOSFET for a granted, right? And we start designing circuits. But the thing is that the designing of MOSFET is itself a very difficult task. Okay, people are doing humongous research in designing that single transistor itself. Okay, uh, currently I think the latest technology is 5 nanometer, and 4 nanometer is already out, and the 3 nanometer technology will be out in another maybe 1 year by Samsung and TSMC. But the thing is, what's ahead, right? So what nanometer ahead? So Intel has shown that, okay, we are going to 1.8 nanometer, that is 18 angstrom. And again, apart from that, I think the Samsung has showed that, okay, they will be going in 2 nanometer, and all of this actually has new kind of devices. Okay, they call this as complementary field effect transistor. Okay, am I audible now? Okay, yeah. So yeah, what I was discussing that, yeah, what I was discussing, that the new kind of devices, the complementary field effect transistors. Okay, and this complementary field effect transistors will be in the latest advanced technology node, where the NMOS is actually built over the PMOS, right, such that you reduce the area footprint. So this kind of new innovations are going on in the device community, and this is very important to take care of. Okay, so yeah, that's the reason this course becomes extremely important in that regards. Now I will go to another course, which is analog electronic course, right? So you there are three verticals, or three major verticals in VLSI design. The one is digital design, right, which I have already discussed, and whatever you have done in the part of this course, that was the digital design part. Okay. The second was the electronic devices, right, which I've earlier discussed in the third course. That is the device physics aspects of it. The other aspect, or the other spectrum, is what we call as analog design. Okay, so analog design becomes extremely important because if you want to communicate with the real world, okay, so real world is not digital. You should understand that. Okay, you are hearing my voice in the continuous time, right? Although it has been processed in the digital hardware, but the input which is taking is actually analog. Okay, everything is analog. You see the nature, there is a gradient, right? There is nothing like 0 1 0 0, right? uh, Sorry. Yeah, so there is nothing like 0 1 0 0, or something like which is actually digital in nature, right? So everything here in the world is analog, right? So wherever you want to communicate with, say, nature, you have to go to analog, right? So suppose you have a sensor, right, which actually detects, okay, how far you are from. So you have an infrared sensor, or you have an accelerometer, right, which just checks the speed and all, right? You can have a temperature sensor and everything you can have, right? All of this to work, right, you need some analog circuit which can capture these analog signals, right? The processing of the analog, and then, okay, you send convert it into digital and do the further processing, right? So for that aspect, this analog electronic circuit course becomes very important, and Professor Santi Pawan is maybe I must say he is one of the greats in the analog design, and he is a leading analog researcher in India. Both Professor Santi Pawan and Professor Nagendra Krishnapura from IIT Madras. You can follow the works of these two professors. They are doing some wonderful works. Okay, and they are one of the most prominent names in analog design across the world. So yeah, so that was the fourth course. The fifth course, and which is very interesting course. So when I was doing microfabrication, right, I have actually followed this course in a very greater detail. I have actually notes of this particular course, and that's actually I have notes of all the courses because I've done all the courses. That is the reason why I'm suggesting you guys to do all of these courses. So the fundamentals of microfabrication, micro and nano fabrication, by Professor Sankar Kumar Selvareja and Professor Susovan Avasthi. Both are from IIT Bangalore. And see, I think you should understand microfabrication by remembering the slide which I've shown for the layout, right? So you design a circuit, right? You design a circuit using RTL, using Cadence, or whatever tool you have. Then you make the layout, right? So you lay down the metal wires, right? You do the communication, you do the connection and all. But the question is, right, so how does the finally it will be translated into chip, right? So that's the biggest question you should have, right? Eventually, whatever you design as a VLSI designer has to be translated into a chip, right? It has to be translated into a chip, right? And that process is called as the fabrication, right? The micro or nano fabrication, and that is typically done by a foundry. It can be TSMC, it can be UMC, it can be Intel, right? Global foundries, or we have so many foundries available, right? And there are various sets of methods which goes on while designing the chip, right? So you have to actually print this nano scale in your wafer, right? How do you do that? You do using lithography, right? How do you make the boxes? How do you cut the gates and all? You can do etching. How do you deposit, right? You do deposition, and various techniques are available when you start understanding the microfabrication, right? And microfabrication again becomes very important, all right, because that's the lowest level. And so by doing this course, right, so I realized that if you want to have a very maybe prime example of pure engineering, microfabrication is one of the thing which is pure engineering, right? So when you will do this course, you will realize what are the things these engineers have done to realize, okay, to print dimension at such a nano level. Okay, you are printing 20 angstrom or 15 angstrom, right? It is marvelous, and the pure engineering, you will start appreciating this course, right? And I highly suggest you to take this course so that you understand the lower aspects of it. And people require, or the companies require, people who understand the top level, the middle level, and the bottom level, right? So for that understanding, this course becomes extremely important, right? So again, this course is also a part of gate, right? So maybe one or two question every year has been asked from the micro and nano fabrication. So just a motivation if you want to give a gate exam or not. But it doesn't matter if you want to have a career in VLSI, right? This becomes one of the very important course. The sixth course, I think you guys are already doing the design and analysis of VLSI subsystem, right? So we were actually at the very basics when I've discussed the first five courses. When you go to the advanced level, it becomes the VLSI design, right? So we have actually learned a lot of things here, right? I'm not going into greater detail because we have been doing this course. Now, next course, and again, one of the very famous course because the professor is very famous, right? Professor Indranil Sen Gupta. I've already shown one of the courses from digital design, right? And this course is again marvelous, right? So, if you want to do understand the back end of the design, the physical design, okay, how does at tool level these chips are designed, right? How does everything is being laid out and all, what kind of algorithm that is being used over there, right? And how these tools work, right? So all of these concepts will be actually cleared by this VLSI physical design course from Professor Indranil Sen Gupta. Okay, so yeah, this is one of the very important course that you should be doing, right? I have not listed many courses, right? I have only listed 11 courses, right? Which is actually will actually make sure that okay, you cover the entire spectrum of the VLSI design, right? You have a very detailed theoretical understanding of the VLSI design, and it will also give you various practical knowledges, what kind of practical challenges you face while designing the VLSI. Okay. Uh, One course I have included over here, right, and which I personally feel was a very great course when I have done this VLSI CAD Part 1 and Part 2, Logic and Layout. Okay, this course is from University of Illinois at Urbana and Champaign, and this course is available on Coursera. Right, so all the courses which I've shown earlier was available on NPTEL. Again, this course you can do freely from Coursera. If you want to say get a certificate, you can give an exam. So that's a separate thing. But this course is again. So here also, just like the previous course from Professor Indranil Sen Gupta, you will learn um, how this CAD tool works, right? When I talk about CAD tool, the tool which are used to design VLSI circuits, okay, and this course will actually give you the algorithmic aspects of it, okay, how does things work, and these are one credit course you can cover in a day or two. And once you do this course, you will realize and you will understand the importance of EDA, the electronic design automation, in the VLSI design. Okay, how does these tools are being designed and how good they are, right, while designing the VLSI circuit. The ninth course, and this I have found a gem. You can call this course a gem because yeah, this kind of courses are not available anywhere. And IIT Gandhinagar is one of the very few institute which teaches the full RTL to GDS to a student as a part of this course in India, right? But for you, this course is openly available online, right? And I think NPTEL is also coming up in the next semester a similar kind of course. But this course which I have, so you can go to YouTube and search, and I have also provided the link over here. The thing is, there are only 12 lectures, okay? Each lecture is of 2 hours, right? And it will start with very long and it will go to the final layout, right? So that level of details you will understand. And whatever the topics which I have discussed in the last class regarding these digital IC design, right? The very log, the RTL design, then you do the synthesis, then you do the placement, right? Clock tree synthesis, routing, everything will be discussed in a very great detail in this course, right? So while doing after doing the VLSI design course, this is a natural extension, right, to go ahead. Okay, so the physical design one from the Professor Indranil Sen Gupta, then this digital VLSI design course. There will be multiple overlap between both of these two, right? But you should do both the courses. And the best thing about this is the PDFs and the notes are openly available. You can download. You should not write the notes, right? It will take time. So you just understand the concept, and notes will be available to you from the online itself. Okay. And last two course which I am including over here because whatever courses I'm actually showing as a part of my LinkedIn post that I've already shared, and it became actually viral. Yes, you can have my contact detail, right? I have my email. You can connect with over there, and you can also connect with me in the LinkedIn, right? So I generally answer queries of all the students who try to connect with me over there. Many students ask questions regarding VLSI and all, right? And this the post I have created, and the list of the courses was for them only, right? And because I have promised you that, okay, in the last session we'll be discussing, okay, how do you build your career in the VLSI design, and what are the things you have to do. Okay, so this I am talking about the theoretical aspects of it, right? And the two courses which were suggested by everybody in the LinkedIn, and okay, these two courses I should include. One is digital IC design from Professor Janaki Raman, right? So I forgot about this course because this was a wonderful course, right? Professor Janaki Raman is one of the great guy in the digital design in India. And yeah, you should take this course. It will have an overlap with the previous courses, but again you can quickly complete if you have a basic understanding, right? And one of the things which India lacks by a very large margin as compared to United States or China is electronic packaging and manufacturing, right? So once you have a chip, okay, how do you package it, right? So that becomes a very important aspects on the VLSI design, right? And it is the advanced level course whatever I'm talking about, right? And it doesn't matter, right? Here at IIT Gandhinagar, we take second year and third year students, they do this kind of courses, although we call this as advanced level course. But the thing is, to do this kind of courses, you should have a basic understanding of digital circuit, analog circuit, semiconductor devices, and the basic VLSI design. Okay, so these were the list of 11 courses which you should do to have a complete understanding of the VLSI design. How much time it will take, maybe a 6 month or a year to complete all of these courses. But trust me, right? After say 6 months or a year, once you have completed these courses, you will be enlightened with the knowledge in the VLSI design. Okay, so this was the courses part. If you have any questions till now, you can ask any questions. Okay, so I think I have comprehensively covered all the aspect. Right now, yeah, comes to very important part. I think most of the you are here for this thing. Yeah, so it is, I guess, lagging. Just a minute. Okay, Hardik, I will take your question at the last. Yeah, I will answer these questions to you. Okay, let me just see. Okay, so yeah, this is one of the very important slide, and again, this is another part of my LinkedIn post, right? So what are the job profiles which are available in the industry. Okay, and I have been working with maybe 50 to 60 students during my PhD, right? Currently I'm also currently I'm working with maybe 10 or 15 of them. And whoever actually joins VLSI industry actually joins one of these positions. Okay, it can be a logic design, right? So it can be a logic designer, as a logic designer. It can be a memory designer, right? As a memory design engineer, right? So you can be only a design engineer also, right? So various company have a post only of design engineer, right? So it can be logic design engineer or memory design engineer or design engineer. Okay, there is one more that I have not added over here is CAD design engineer, right? So you design the tools. Then the second type of job is verification engineers, right? So either it will be a verification engineer or design and verification engineer, right? So DNV, they say. Then they have STA engineer, right? So we have discussed about static timing analysis in a very greater detail in one of the lectures, right? And please go through that lecture, right? So which I have covered, where I have covered the static timing analysis basic concepts, right? So your job just will be to do the timing analysis in a greater detail, because it becomes the one of the very key component of VLSI design and whatever chip you make. Okay, then you will have DFT engineers, okay, design for test. So what are we doing currently is that, okay, whatever chip you design, there should be some test circuit to test this chip automatically, right, without manually testing it, right? So whenever the chip will come and it will have we have the fabricated chip with us, we just provide some signal, and there can be an automated testing. And yeah, every company is actually hiring the role of DFT engineers, right? If you go and just see the DFT engineer, NVIDIA, a couple of my students are working. So the students who have worked with as the DFT engineers in NVIDIA and Qualcomm and all, right? And yeah, this is one of the highest paid job in the VLSI domain, right? So you can get maybe a base amount of, say, as a BTech, 16 lakhs, and a CTC of 35 lakhs, right? So in all of these domains, whatever I've been discussing. Okay, these are the numbers which I get from my collaborators, my students who have been working in VLSI domain, right? So if you join after BTech, right, you will be able to get a job which will actually pay you maybe 14 15 lakhs as a base amount. The total CTC can go as high as 25 to 30 lakhs. If you join after MTech, you will get a base amount of 17 to 18 lakhs, and total CTC can be around 30 35 lakhs kind of thing. And if you join around about after PhD, right, the base amount will be 20 to 25, maybe more than that. And the CTC will be maybe around 50 to 55 lakhs. Okay, that is in India. Okay, so that's how well the VLSI engineers are paid, right? The thing is, you should require greater skills to crack this kind of jobs. Yeah, no problem, Nachiket. You can watch my recording. It will be uploaded in the YouTube just after this session. Okay, so regarding what I was discussing about the jobs and what kind of packages you have, and if you want to say join abroad, like in United States, so just if you join here in Europe, right? So I am currently in Europe, and I've seen that, okay, people are paid 70 to 80,000 euros um, yearly, right? So that will actually translate to around 80 to 90 lakhs in Europe, right? If you are an engineer over here, VLSI design. And if you go to United States, they pay you more. That is 100K to 120K. That will be around 1.2 crores of annual salary. Okay, so you should realize that, okay, the living expenses are pretty high in the Europe and uh, in in Europe and United States, right? That's the reason the higher salary is being paid, right? So if you want an apple to apple comparison of okay, what a 25 LPA CTC will look like in terms of US. So if you are getting a 25 LPA in India, right, to have a same lifestyle, you should have at least say we say 90 to 1 cr, 90 lakh to 1 cr in Europe or US. Okay, that's how the comparison should be. Okay, so India is paying pretty well and very high in that regards. Okay, so this was just a basic information because everybody wants to know, right, what kind of salaries and you do expect when you join this kind of industry, right? So I have told you about India. I also told you about Europe and US. Okay, coming back to the positions which I'm talking about was the physical design engineer, right? And the physical design engineer is actually taking care about the back end of the design, the layouts and all. And out of all the jobs, right, which I've shown, the physical design engineers are the highest paid, right, among all of them, right? Because the job of the physical designer was is to actually make the chip work, right? So do all kind of testing and just to make sure, right? It can happen that if you are a physical design engineer, maybe in Samsung, I was discussing with one of my seniors over there for 2 months, right? They have sleepless night to make sure that the chip whatever that has been designed, right, passes all kind of tests, right, at the simulation level, right, and do extensive testing, right? Huge team will work on that, and then the chip will go, and then you can take rest for another month, right? So that's how the physical design engineers work. Now the question is, right, what kind of skill set you have, right? So what I have done, I have actually gone through these profiles in LinkedIn. You can go also in the LinkedIn, just search for all of this profile. You will actually find out, okay, there are various job which are available. Now the thing is, okay, what kind of skills you should have, right? So I have actually listed down, sorry, yeah, I have listed down some of the common skills, right, which are actually required across all of these jobs, right? It doesn't matter whether you are applying for a physical design engineer or a logic design engineer or a memory design engineer or stage engineer, DFT engineer, doesn't matter. These 10 skills, right, you should have irrespective of whatever job you are applying. The very first is a knowledge of an hardware description language, right? It can be VHDL, Verilog, or System Verilog, and from there, the first course from Professor Indraneet Sen Gupta, the second course which I've shown, becomes extremely important, right? Then, so you should understand, right, why I have shown you those 11 courses, because, right, I know the job market, right, and people who are working over there, and whatever the company expect from you, right, based on the study on the LinkedIn. You see, the second is the knowledge of digital and the analog circuit design, right? So that is the another skills you should have. And you do the courses, and you will see that, okay, you will start getting expert in it. The third is, which is actually very difficult to access if you are outside an NIT or IIT, right, in India. But there are various open source alternatives. So you should have expertise in some of the EDA tools. These are generally tools from Cadence, Synopsys, and Mentor Graphics. These are the three big players. But I have a post in the LinkedIn regarding this open source EDA, right? So you can go to that particular post and you just see, right, what are the open source tools which are available, and how you can get the same level of expertise in using open source tool, right? But when you join the industry, then you can start using your own and this kind of tools. Okay, so that's the third skills every company actually wants from you, that okay, you should know how to use tools, right? You should not be scared of using the tools, right? So that's pretty much sums up the thing. The fourth is semiconductor manufacturing and the process technology, right? So there, the fifth course from ISC Bangalore come into picture, where you what you should understand the microfabrication, how it is being fabricated, right? So that's the fifth course. Now, the fifth point is knowledge of low power design technique and methodologies, right? The entire VLSI design, which we have discussed, a very big portion was from low power design. So the course you are doing is becomes one of the important courses when you apply for a VLSI job. Okay, so the course from the Professor Madhav Rao, for which I am currently the TA, right? The sixth is experience in ASIC design flow and methodology. So from here, for this, the two or three courses, one was Professor Indranil Sen Gupta physical design course. The second was from Professor Adi Teman, right? The RTL to GDS course, right? And the VLSI CAD layout course becomes important for you. Okay, so this is this skill you should have, right? You should have an understanding of a greater detail, right? And it won't take much time to have or familiarize with the understanding, right? Now, the seventh is you should know some of the industry standard protocols, right? This I have not discussed in the VLSI design course. It was actually beyond the scope of the VLSI design course, but you should go over the internet and you should search these protocols: PCI, USB, DDR, Ethernet, right? There are multiple protocols like AXB, right? AMBA, and there are SPI, I2C, okay, UART. These are communication protocols you should know, uh, and they should have actually implemented at least one of them using Verilog, right? So that's minimal ask from you, right? If you are looking, okay, what kind of project I should design using Verilog, right? Yes, this is the project you should design, right? You take any one of this protocol and start implementing it. There are open source uh, places, open EDA playground, where you can design and simulate and synthesize your design over there, right? But having an understanding of these standard interfaces and communication protocols become extremely important for you. Okay, now the eighth thing, which is a must, right? So it doesn't matter, right, whether you are at class 8th or you are doing a PhD, you are an electrical engineer or you are a biological engineer, whether you are a doctor or a lawyer, it doesn't matter. You should know programming. Okay, so programming has become, okay, Hardik. Yeah, I think now it will, just to wait. Yeah, I'm extremely sorry. Audio is lagging. Yeah. I hope now I am audible. Am I audible? Thank you. So, okay, I repeating the eighth point, right? So, what I was saying that doesn't matter if you are a class 8 student, right, or a PhD, or a biological engineer, or electrical engineer, or computer science engineer. Doesn't matter you're a lawyer or doctor. You should understand the basics of programming. Okay, so programming becomes extremely important tool for you, right? So you think programming as a way of communicating with computers, right? So you have learned the English and Hindi language to communicate with people in India or outside India, right? So that's how you communicate with people. Programming is a way to communicate with computer, right? It doesn't matter who you are, you need a way to communicate with computer, right? In future, with the advancement in AI, machine learning, and this chat GPT kind of thing, right? Things have been revolutionizing, and if you don't understand the programming and you do not have the skills, right, you will be lagging behind by a great extent. Okay, so that's the reason you should have an understanding of programming, and you should know how to do scripting using these languages like Python or Perl or Tcl. You should be familiar with. Okay, so for There are no courses as of I know of regarding the protocols, but I will just go and search if there are courses. I can share the link in the WhatsApp group. Okay. The so That's the 8th point about the programming. Now ninth is, okay, every engineer that has that, right? Because then only you are an engineer, strong analytical and problem solving skills, right? So quality of that's a must quality of an engineer. Okay. So the next point is communication and teamwork skills. So it doesn't matter. So it does matter, actually. It does matter that, okay, you should have a soft skills, right? Like, okay, how do you communicate with people, and how do you actually work in teams, right? How do you guide people? This kind of skills also you should add in your profile, right? So that's the soft skills part, right? The other skills which I've discussed were the technical skills. But people, if you are working in team, you should be a team player, right? So yeah, or if you are assigned some responsibility, you should be able to lead the team. That kind of attitude you should have, right? Create that kind of mental space, right, where you can work with team, or you can work alone, or you can lead a team, all sorts of things. Okay. So these are the basic 10 skills, right? Which is actually common to all. There are specialized skill. You can go on the internet or LinkedIn. You can start searching for them. But these are the basic skills you should have to get a job in a VLSI domain. Any questions as of now? Okay, no questions. I will just conclude my this session by having four different research areas which I am working on here at IIT Gandhinagar, and these four research area, pretty much everybody is working on at here at India and the different IITs across the world, like institution like MIT, Stanford, right, and the UC Berkeley. Here at Europe, it is Zurich, the KU11, right? Everybody is working on. The very first research area is designing hardware accelerator for machine learning. Okay. Okay, I have a question that why scripting is important to learn, right? So the thing is, scripting becomes important that, okay, you want to do repetitive tasks, right? So suppose you have a tool, right, which does the synthesis of a Verilog design, right? And you have 2 lakh of Verilog designs. Okay, somebody has made 2 lakh Verilog designs, right? And you want to synthesize all this design and just get the power, area, delay result, which tool will obviously give you if you do the synthesis by your hand. You cannot do the synthesis of 2 lakh design by your hand, right? So that is not practically possible, right? So what you will do, you write a script, right, which will automate or which will directly call the Verilog design, which will do and which will run the tool by automatically, and then it will generate the result and it will save the file automatically, right? That's how scripting becomes very important, right? You want to do the layout of, say, all of this design, right? You cannot do it manually, right? One single engineer cannot do that particular job. For that, you have to take the help of the programming or the scripting language to automate the flow. And please understand, right, this is a very important point I'm making. VLSI is 10 to 20% of design, or whatever 11 courses which I have said. The rest 80% is scripting, right? So if you get into VLSI industry, you will realize that, okay, what level of scripting people do, right? Everything is automated, right? So the design flow is automated. How do you design? Everything is automated, such that there is less and less error from the manual intervention. Okay. Now coming back to this research area in VLSI, the first was the designing hardware accelerator for machine learning. Okay. So this machine learning workloads, like there are various things which is going on in machine learning, and one of the prime example is ChatGPT, right? So you might be very astonished to see the power of ChatGPT, what it can do, right? It can do pretty much everything. You ask ChatGPT to write a very log code of pipeline processor, it will do it for you, right? You ask write a test bench for a pipeline processor, it will do it for you. Okay. You ask ChatGPT to, okay, I am a lawyer, right, and I have been in this case, right, and can you help me with this regard? It will act as a lawyer for you, right? If you ask ChatGPT, okay, this is the disease I have, right, and what are the sets of medication I should take, right, it will actually give, it will become a doctor for you, right? So the thing is, you should understand that how powerful the artificial intelligence is, right? And this is my belief in future, that okay, most of the jobs which are redundant, which requires say redundant skills like copywriting, the writer, and everything, will actually be replaced by AI and the tools like ChatGPT, right? Will human skills will be replaced by ChatGPT? Yes, many of the human skills will be replaced by ChatGPT, and there are already been replaced, like the people who do copywriting, right? The people who do the technical writing and all, they were in a greater demand, right? But now the thing is, if you ask ChatGPT, it will write a paragraph for you, it will write a book for you, right? So that's how it is becoming, it becomes important, right? So that's the thing, right? The thing is, you should constantly adapt the skills, right? Constantly try to solve more complex and complex problem, otherwise your whatever skills you will have, right, that will be eventually replaced by AI, right? And you will no longer have jobs or the things, it can happen in future, right? And I'm not scaring you, this is the truth, okay? uh, Whenever this kind of technology comes, what you, as a human, you should do, right, you should upgrade your skills such that you are able to solve more complex problem which AI cannot do, okay? So that's how the future beholds, right? And I'm pretty much excited to just see, right, how the future will pan out after this the advancement in the chat gpt, the all the LLM models from Facebook, Google, and this open AI. Okay, so the thing is, okay, this algorithm seems extremely astonishing. Okay, there is a thing. The thing is, it is actually running on some hardware, right? And you realize if some model can do such a complex thing, how big that model, how difficult it is to process that kind of model it will be, right? So at the back end, you have to design systems which can run this chat gpt kind of model. You type something and it will take some time to respond, right? Why it is taking some time to respond? It is going and it's processing in the hardware, and then it is giving back to you, right? So the question is, okay, how do you design this hardware for machine learning, and what kind of things you should do? Here at IT Gandhinagar, we work extensively on designing hardware for machine learning, and pretty much every IITs and all the top universities work on that. The second research topic is in-memory computing. I will go in greater detail in a coming slide. Third is approx computing, and the fourth is design of physical and kernel function. Let me show you some of the chips, which is an hardware for accelerator for machine learning. The only thing I think you would have heard of is Google's TPU, but if you have not heard of, you should go and just see, right? Google Tensor Processing Unit 4, right? This is one of the specialized chip that has been designed by Google, right? You might think Google is a software company, but it is not, right? At the back end of that, Google do extensive hardware design, right? You can apply for a job in Google as a VLSI design engineer, okay? Google Bangalore is actually working in the design of this TPU, okay? So and they have pretty much opening and all, right? The thing is, every company design their own hardware. Amazon also designed the Tesla, the Samsung, IBM, Nvidia, and all of this for running machine learning workloads, okay? Machine learning algorithms. There are some of the startups which also does that. These are the name of the startups, and universities like MIT, KU Leuven, KAIST, Tsinghua, here at IIT Gandhinagar, IIT Madras, right? IIT Delhi. The people are actually working in the designing hardware for machine learning, right? The goal is to, okay, how fast you can make this AI algorithm to respond, right? You want it, okay, as soon as you type, the chat gpt should give you instant response, right? In fraction of second, it should complete everything for you, but it takes time, right? Now, the why it is taking time, because the hardwares are not efficient, okay? So although it is very efficient past, although it is very extremely efficient from the past, but it is still not efficient now, such that you can get a millisecond of response. Okay. Second is what we call as in-memory computing. Okay. So all the current computing system, and this is my PhD research, right? One of the key topics in my PhD, hardware for machine learning was again one of them, but this is I'm very close to. The thing is, okay, every system you have has a processor and a memory. Okay, you will have an SD card, you will have a RAM, you will have an hard disk. All of these are memory, and then you will have a processor, right? So whenever you are actually say running a game, okay, you are playing a game. What happens? The game is stored in the memory, right? Where in your SD card or somewhere, it will go. The data will go to the processor. The processing will be done, and again sent back to the memory, right? This is how the conventional system works, and this system is known as von Neumann system. Okay, the problem is, right, so the memory is fast, the processor is fast, right, but the problem is this data movement takes time. Okay, and this consumes a lot of energy, right? Just take an example that, okay, you have a factory at Kerala, right, and the raw material comes from Jammu Kashmir, right, and every day what you have to do is, and the market is again in Jammu Kashmir, okay, because they produce raw material, and there all the things are being used. So what you do, you take the raw material, you send it to Kerala, then you process it, and you come back to the Jammu Kashmir and sell, right. What is the problem with that? Most of the money actually goes into the transportation in the between the Kerala and Jammu Kashmir, right? Same happens with the your mobile systems also. Most of the energy actually goes with the transportation between data and memory. So the idea is, right, if I take the example, right, you make the factory in the Jammu Kashmir itself, right? If you make the factory in the Jammu Kashmir, then what will happen that, okay, the transportation cost will actually go down. Only you will have the local transportation cost, right? And that will actually save a lot of money for you. Same idea here is, okay, you make your memories more intelligent, right? You do computation inside memory, right? You do processing inside memory and make your memories more intelligent. So it makes much more sense where the data resides, right? Do computation where the data resides. Okay, so this whole domain is called as in-memory computing. IIT Gandhinagar is one of the forefront in India in the in-memory computing. There are a couple of more IITs like IIT Roorkee who works in the digital design. IIT Bombay also works in in-memory computing at a device level, right? And a couple of more IITs are working on that regards. The next is what we call as approximate computing, and for having approximate computing, I had this example that, okay, these are three colors, right? I can see these three colors, right? By naked eye, can you see the difference between these three colors? Okay, I know your answer, that the answer is no, right? You cannot differentiate between these three colors, but you can see the encoding for this tree is one is 255, the another one is just let me take this, right? One is 255, another one is 254, another one is 253, right? So you see, despite having different encoding, you still get to see the same color, right? So the thing is, even if your image has some kind of error in the encoding, it will actually not degrade the quality of the image. Okay, so from that concept, we come with the idea of what we call as approximate computing. Okay, so this is another two images which I have taken. One of the very famous image in terms of image processing. The question here is, this is just the question is for you. There are two images. Can anybody tell me which one is original? So first one or the second one? Just type your response. The right one. Okay, Hardik is saying the right one. What about others? Others, please respond. Right, very simple question, right? The right one, Asim, right? It is pretty obvious, right, by looking into the figure that, okay, which is the original, right? The right one, everybody is saying that, but the thing is, yeah, Tejas is also saying right one, yes is also saying right one, right, because of more clarity in the image. But let me tell you that the left one is the original image. Okay, not the right one. The left one is the original image, and I have done some approximation, and the right one is an approximated image, right? So the thing is, it is not like that. Okay, if you, and I will show you, okay, I will just show you, this is the exact image. Okay, you see, all the pixels are 162, and yeah, very nicely arranged and all. What I've done, I put some approximation. I made 162 to 164, 159, this kind of approximations I have done. I'm not sure if it is been shown over there. Just 1 minute. Yeah, you can see, right? So 164, 159, and 162 and all, right? So you see the right one is approximate, but it is looking much better to you, right? So the idea is, right, if your hardware is also approximate, right, you can save a lot in terms of energy, power, and area, because all of this image processing, you cannot actually visually differentiate between exact and approximate image. Okay, so the idea is to make hardware more energy efficient, and this is, I have also taken an example. You can enhance the image, right? So this was the original image. You can enhance by taking image power root 2. Image is not nothing but just matrix. All the component you take the root 2. If you write 1.414 or you write root 2 value 1.41 or 1.4, you can see, right, I'm reducing the precision, but you see there is no change in the image quality. Okay, all three images on the right actually looks pretty much same. Okay, so there the idea of approximate computing comes into picture, that okay, if the image are or the application are error resilient, right, if it can tolerate error, why don't we design hardware which are approximate and take lesser energy, area, and power? Okay, so this is a very interesting domain people are working on, right? And most of the hardwares are now approximated to lesser number of bits. The last thing which I want to show you, just let me see. Yes, this is what we call as physical uncallable functions, right? One thing which I have discussed was the process variation. Okay, in I think so some of the lecture, that okay, even if you fabricate a transistor with say VTH equal to 500 millivolt, it can happen that one of the transistor has a VTH of 450 millivolt and another has 550 millivolt, some has 500, some has 472 millivolt, right? It can happen because of the process variation, and you don't want these things in your device, that okay, this much of variation is there, because if the threshold voltage is varying, then the current will change. If the current will change, your performance will change, right? That is a problem with the normal circuit. But what you can do, you can utilize this variation to design what we call as physical uncontrollable functions, right? What we call as physically uncontrollable functions. So suppose you have this kind of SRAM memory. Okay, this is what we call as memory, right? And you have so many of them. Okay, so individual all dots are saying SRAM memory, right? So when you design, all of this SRAM memory will have different. All the transistor will have different threshold voltage, and you see this is a cross couple latch, right? So this will either be 0 or 1, or this will be 1, or this is 0, right? As soon as you power up this device, right, the stem will go either 1 or 0, right? And you don't know what state it will go depending upon what VTH of the transistor you have. Okay, so and this people use to design these things, right? And what happens that okay, suppose I have a laptop which has an SRAM, right? For me, if I read this row, the data pattern will be different. For you, if you have a same laptop, but the fabrication has the variation, right? For you, the data pattern will be different, right? And in that manner, you can have your unique keys corresponding to your laptop, right? And then this will help you to secure your laptop. People are working on these things at the hardware level. We call this as cryptography hardware security, right? uh, I have just given you four research example, but if you are interested, right, you can go look for the top conferences and journals. You just see what kind of wonderful research are going on, right? These are very few, right? These are maybe four out of 500 or 1,000 research topic which are going on in the VLSI domain, right? So I hope you have learned something from this session, right? Now, if you have a questions, you are free to ask. I will be happy to answer all the questions. One question was, okay, how do you prepare for exam, right? You go through all the lectures, go through all the assignments, and go through all the questions which I've discussed over here. Okay, this will pretty much help you to clear the exam. Okay, so I think that will be sufficient enough. what you can do, you can go to Google, try to solve many question. You can take the reference book, the I think the Vesta Harris and the Rabe's book, and you can solve questions from them. It will help you to crack the exam. Okay, so that, but whatever that has been taught in the class, and the assignments, and this session will be sufficient enough to pass the exam with flying colors, right? Do prepare hard for that. Any more questions? Yes. What question you have, Tejas?
Sir, as we know that currently there is a time of quantum computing, so
Yes.
is VLSI has some effect on that or not?
Yes.
Or is
So
like it's an another
quantum
branch
computing
for.
is a part of VLSI design, right? So, um, see, the thing is, traditional computing systems are coming to an end in terms of scaling and all, right? And there are various problems in the world, right, which cannot be solved using the classical phenomena or classical computers, right? So then people are actually working in quantum computing, right, where you understand the physics behind the application which you are running, and whatever so see, when you go to the quantum domain, it will actually be hard for you to realize, but the thing is, okay, how does quantum computer works? There are no zero and one in quantum computing domain, right? So just like in digital, you have a zero or one to differentiate between the two states. Actually there is some intermediate states, right? And there are what we call as qubit, which actually defines the power of the quantum computers, right? And the hardware that has to be designed for the quantum computers is actually one of the sub branches of the VLSI design, right? And you will realize you will need an extensive knowledge of semiconductor devices, microfabrication, the semiconductor physics, to understand the quantum computer, right? And what people are doing, people are designing the complete stack, just like what we have in the digital design, the RTL to GTS flow. People are designing the programming language for the computer, quantum computers, just like Verilog, a different quantum Verilog, you can say, right? It is not there, but yes, people are designing like that. People are designing a placement physical design tool for quantum computers. So yes, quantum computers is well a part of VLSI design, and if you want to take a future in the quantum computing, it is one of the great areas to go ahead, right? Indian government has giving a lot of push to quantum computers, right? Recently read a report of 6,000 crore has been invested in quantum computer. Earlier I have seen a report of $1 billion investment in quantum computing in India. um, yes, so yeah, it's a part of VLSI design. As a VLSI engineer, you have a lot of impact to make over there. Okay. Any more questions? Yes, Ashin.
Sir, sir, my question is, what are the design challenges when we shift to a particular node from like 5 nanometer to 3 nanometers? And what are the physical challenges, physics applied in that? And
Okay.
how researchers complete the task of shifting from a particular node to a smaller node?
No.
And why we don't shift from a smaller node and make the silicon size bigger?
Okay. Okay. Make the silicon size bigger. Okay. A lot of question, but I think I have uh, understood what you are trying to ask. Right. The first thing is, why do we do scaling? Okay, that's the first thing we should understand. The scaling is being done to reduce cost. Okay, to reduce cost, right, and get higher performance, okay, and higher power benefit, or lesser power, you can say, right, lesser power. So that's the basic idea behind scaling. Okay, so and this is the basic idea behind shifting from one node to another node, right? When do you say that, okay, I'm shifting from one node to another, 5 nanometer to 3 nanometer? If you have, say, substantial performance benefit and the power benefit you have. The thing is, why do we not go to larger area? Because the area is the cost. Okay, you should understand that. Okay, the lesser the area, the lesser the cost is for designing the chip. Okay, and you can pack in more functionality in the same area. Okay, now coming to the challenges, what you have, that okay, you are actually now printing in nanometers, right? Very narrow nanometers. You range from 5 nanometer not 5 nanometer, 10 nanometer to say 18, even if it is 5 nanometer technology node, the dimension is 10 nanometer to 20 nanometer. Just imagine to fabricate this 10 nanometer, how difficult it will be, right? You cannot visualize 10 nanometer, but you are actually building uh, more than a city, right, in the area of 1 millimeter chip, right? Design challenge comes because you are not able to perfectly print it, right? And because of that, what happens that okay, there are process variations. Okay, because of that, okay, there can be process variations. Okay, and this will become one of the killing factor, and this was one of the killing factor because of Intel has actually lost the race to TSMC from 10 nanometer, because Intel was unable to tackle care the process variation in their 10 nanometer node. Right now Intel is gaining again the retraction, but this became one of the big issue. The second big issue that okay, earlier we were used to getting benefit of say performance doubling every 2 years, right? So that was the Moore's law was. But the thing is, and you get the power benefit of half, if the power reduces to half. It was the earlier case, but now it is not happening because you are at the atomistic domain, right? So if you talk about say 5 nanometer, 3 nanometer, 2 nanometer, the silicon atom size is 5 angstrom or 1.8 angstrom, like that, right? So you are actually designing channel which are only 10 atoms thick, right? So whenever you go to such a lower domain, your classical computing actually doesn't work, right? And all the phenomena becomes quantum. Okay, now if you want to understand the physics and you want to design devices using that, you have to really understand the quantum physics behind it. Okay, how things are working. Okay, what you need to understand the Schrodinger equation. You need to understand all the values and all what happens in the quantum domain, or whatever the things which happens, right? And this becomes pretty challenging, right? So more and more devices are coming in the same area, right? Things are going quantum, and you will realize that okay, you will see lot of effects, right, which you cannot understand from the classical domain. And one of my friend here at IT Gandhinagar is actually working in this advanced technology nodes. She is actually designing nano sheets, and she's trying to understand okay, what are the impacts of okay, whatever the classical things we apply in the device. But if you see the quantum level, things go haywire. Okay, things becomes if I say the threshold voltage with the channel length, if you see okay, there is some kind of variation in the classical domain. This is not same at the quantum domain, right? Because of the quantum phenomena which are going on over there, right? This is second biggest challenge which you have, right? And the thing is, you have to now design tools which will fabricate this kind of the miniaturized device. ASML is doing that a pretty good job, but the thing is, after some time, it will actually eventually stop because you will left with one silicon atom, right? Below that you cannot go. Below that you cannot go, at least from our current understanding, and things will be coming difficult, right? These are the challenges at the transistor level. There are challenges with the interconnects level. Okay, as you're going narrow down and down, many interconnects are coming closer and closer. So earlier what used to happen, interconnects were far away, and if you run something in one interconnect, it doesn't have any impact on the other another interconnect. Okay, now what is happening that okay, I have shown you in one of the slide that okay, when interconnects are so fast that okay, if one interconnect switches, it impacts the other interconnect because they are so tiny, and they are very near to each other, so that the capacitance between them is extremely high, and impact of one actually impacts the other, and it creates errors in the design. Okay, and I will just give one name, what is called as row hammer attack, right? So it's a very famous attack which happens in DRAM, and this is one of the challenges which has come due to scaling. Okay, you may want to go and read that. I hope I have answered your question.
Thank you, sir.
Sir, can you throw some light on in-memory computing?
Throw some light on in-memory computing. Okay, what kind of light? Okay, what are the things we are doing here? So see, the thing is, there are multiple memories which are available. One is SRAM, what we call as cache memory. Okay, so my personal research is, okay, if this is a cache memory, what you do, you have some logic over here, okay, which actually does the computation directly here itself. Okay, so that's the thing we are currently trying to design. The second is what people are trying to do, and we are also trying to do, is, okay, generally what happens, you access one row and you access all the data from over here, right? So if this is your memory, you access one row. What you do, you access multiple rows now. Okay, and you provide input, say 0 1 0 0 from here, then whatever the data that is stored 1 0 1 0 over here. And what will happen, as you activate the four rows, the multiplication will be directly performed over here in the what we call as bit line in the SRAM memory. Okay, and 4 bit into 4 bit multiplication will be directly performed in the memory itself, right? But the thing here is, the voltage you will get over here, you won't get a digital value, you will get a voltage, right, corresponding to that. If 4 bit cross 4 bit result into 256 different level, then there can be 256 different voltages which will come. But see, our current computers understand digital and digital domain, right? Or digital nature isn't digital nature. It understand everything binary. So if you want to say, know what the computation is, okay, whatever the final output is, you put an analog to digital converter ADC over here, right? And you will get a final digital output of 4 bit cross 4 bit multiplication, right? And this is not in only doing, we are doing in SRAMs, we are doing in the DRAMs, the flash memory, the hard disk, everywhere, right? There are many challenges which are associated with it, right? The first challenge is, okay, again, the process variation, right? Anything is in analog, the process variation just kills the design. Okay, um, because, right, the voltage can vary, right? So in digital domain, even if your voltage is going from 0 to 100 millivolt, doesn't matter, right? It is zero, right? Even if your voltage coming from 1 to 900 millivolt, 1 volt to 900 millivolt, it is still, it is one, right? So in digital is pretty robust in that regard, but in analog you have 256 different levels, right? Even if there is a change of 3 millivolts, right, it will just kill your design. Okay, so what I am doing, and this is the one of the work which I have been presenting over here in my Europe trip, right? And I have a presentation tomorrow to Mac, and the idea is, okay, how do you dynamically remove this impact or process variation in the chip itself? Okay, we are doing that. The second thing is, okay, if you are at, say, Ladakh, right, and you are at, say, Sahara Desert, or you are at Arunachal Pradesh, which is very cold climate, or you are at humid climate like Mumbai, everywhere your chip should work, right, in all the range of temperatures. So, in all the range of temperature, the chip should work. With the analog domain, there are challenges that, okay, with temperature, the things start varying. Okay, so now you have to tackle care. Okay, how do you compensate the temperature in the chip design itself? Okay, um, if I so these are the circuit level things we are doing. If I just motivate you, okay, why in memory computing is required, this graph becomes extremely important, right? So the thing is, if you want to access energy from, say, memory, it requires 100 picojoule to 2 nanojoule, right? 100 picojoule from cache, 2 nanojoule for from DRAM. And if I only want to do computation using digital circuits, right, digital circuits, it only requires maybe zero point 0.3 or 4.4 picojoule of energy, right? So you realize that, okay, our computing system doesn't take much energy, rather the data which is coming from the memory is actually having all the energies, or maybe 70 to 80% of the energy actually goes in that, right? And that is the reason we are trying to design our memories which are more intelligent, and you not have to send the data to the processor, rather you compute there itself in the memory. You do some changes in the memory, right, like this, activating multiple rows, and adding a very logic just nearby the memory, and do the computation there and there itself. Okay, so that's the basic domain of in-memory computing. If you want to have a greater discussion in the in-memory computing, I can share a couple of my papers or share a couple of talks which are there online, right? You will able to get into it. Still, you want to have a greater discussion, you can write back to me, right? Or we can have a one-to-one session on that also. Any
Sure,
questions?
sir.
So I hope you should have a, great exam. All the best for the exam. Okay. And it was a nice talking to you guys for last 12 weeks, right? Discussing the VLSI and um, the thing is, I hope you have learned a lot of things from these sessions, right? You should go and recommend people to do VLSI courses and whatever I have discussed, right? Even if somebody is not knowing, right, what should be done, right, you should share this kind of resources with them, right? It's not like that. Okay, the job is not that. Okay, you get yourself skilled. The job is also to get the entire India skilled, right? So you should help others to teach VLSI, right? If you have learned something, just share the resources that people can also get into this particular domain. We need large workforce in the VLSI design in the future, right? All the best for your futures. And okay, Hardik, any questions?
Yeah. Sir, can I have some idea that where can we access the free tools or any open source tools for backend
Definitely,
and
definitely.
front
Yes,
end
yes, yes. So
designs?
I will
If,
share a link in the WhatsApp group. This is the link of the WhatsApp group you may want to have. I think I have the link. I will just share with you. 1 minute.
I joined, sir. I joined this
You
group.
join? Okay, you join. Then I will share the link over here, right? I think that will be you just follow. I should not share, but the thing is, I post a lot of things regarding these things in the LinkedIn, right? So you may want to just follow my threads over there, right? And I will just share the link of my LinkedIn post only, where I have actually discussed all the open source tool which are available in open source PDK over there. Okay.
Okay, sir.
Yes, Tejas, question.
Sir, is there any practical knowledge courses that we can gain like on-hand practice? Because as we all know that VLSI is a very typical and tough course, and we need an on-hand practice. And currently, it's like an intern type timing nowadays in India also.
Yes.
So, is there any courses available or any internship that we can apply
Oh,
to gain that,
internships, I think you are maybe you may be
or any
pretty late
workshop?
if you want to apply at IITs, right? Because this might have already closed. Um, so if you want to apply internship, you should apply at least 4 months back. So that's the thing. But the thing is, at the online level, what you can do. So I will just share the link with you guys. What kind of open source tools are available, and this tool have pretty extensive demos associated with that. Okay, it won't be in the form of a video, rather it will be a form of documentation, which will be available online. Right, you can install all of these tools in your laptop. You can get hands-on in a greater detail regarding all of these tools. Okay, and so if you want to apply for an internship position, you may want to look for startups and maybe companies, right? Go to LinkedIn and just see that there will be enough positions available online. But the thing is, again, to apply for companies and all, you should have your basics very clear before applying, right? There might be some interviews and all. If you want to do research and all, I would suggest that you apply for internship position at IIT. IITs, all the IITs are doing excellent work right here at IIT Gandhinagar. I actually collaborate with maybe 12 or 13 students every semester. I personally discuss or personally guide them. But the thing is, at this moment, I think all the portals will be closed at IIT. Yes, Tejas, please.
Sir, is there any link regarding that IIT internship that you just told us about?
Yeah, there will be. SRIP is the internship at IIT Gandhinagar. You type SRIP IIT Gandhinagar for IIT Kanpur, which I have done in my BTech. That was Surge IIT Bombay. Then from the IIT, sorry, Surge IIT Kanpur, SURG Surge. Then at the, I think, IIT Bombay, it was Eklavya IIT Bombay. And you can also directly write to the professors of the different IITs, top IITs. So the thing is, you should go to the website and you just write summer research internship and you type the name of the IIT in the Google, right? The link will come over there directly. There are 23 IITs. You should just see if there is a link open for any one of them right now. Okay,
Okay, sir. Thank you.
sure. Any more questions? Okay, so I will sign off. That was the last lecture, but still the WhatsApp group I will keep active, right? If you face any difficulty in your future regarding anything regarding VLSI design or anything, right? I'm here to help you, right? Just take a note of that. You can ask anything, anything over there in the WhatsApp. So if you have the WhatsApp group, you will have eventually my number also. You can drop me a message, right? I suggest to drop a message in the WhatsApp group or an email. But yeah, you can have give me a personal message in case of any kind of queries regarding VLSI design anytime from now to till I leave. Okay, so I'm open to you guys. Okay, thank you, thank you for joining this session. Maybe we'll meet in another course or maybe we will meet sometime offline. Okay, that's all. I will just sign off.